and this is because in metallic nanotubes, you have some electron-phonon coupling, special electron-phonon couplings, which will broaden the peaks. So you see that with Raman, you will be able to study selectively semiconducting or metallic, and you will be able to study selectively different kinds of diameters just by tuning your laser light and choosing the good laser light which corresponds to the resonance of the nanotubes you want to study specifically. So this is the first reason why Raman has been widely used for studying nanotubes. It's because it allows you to choose the nanotubes you want to study by tuning the laser light. Let's look at the other Raman peaks. The first ones were this carbon-carbon stretch that we also call G-band because you can see the same peaks in graphite. So G refers to graphite. We call this CC stretch, carbon-carbon stretch, G-bands, because you observe similar signatures in graphite. This is not the only interesting contribution to Raman. There are at least two other widely used peaks to characterize nanotubes. The first one is this band, which we call D-band, and here D refers to defects. We call that D-bands because this band is not allowed for ideal without defect nanotubes. If a nanotube doesn't have any defects, it has only sp2 carbons, and when you have sp2 carbons, you cannot see this band. So the only case where you see this band, this D-band, is when you have sp3 carbons in your samples. You can have sp3 carbons either if you have defects on your nanotubes, or if you have impurities around your nanotubes. For example, amorphous carbon, or nanoshells of carbons, or defective graphite. So you will observe this D-band only if you have defects on the nanotubes, or if you have impurities around. I will just make a small focus on the origin of this band. So it's not mandatory to understand that to use the D-band to characterize nanotubes, but it's interesting to know where does this D-band come from. Actually, it comes from what we call a second-order process, or a double resonance mechanism. I will just show you one slide on that, just to explain you why we observe such a band. So here, these are sketches which explain us the resonant Raman phenomena. Let's first look at the left part. The left part corresponds to what we call the G-band, corresponds to the simple resonance effect. So we said that we have resonance when we can absorb light and send one electron of the valence band to one state of the conduction band, one eigenstate of the conduction band. So here, the sketch represents the dispersion curves of the nanotubes that we studied yesterday. So the dispersion curves close to the Fermi energy can be considered as linear. So you consider that your resonance corresponds to a transition from this curve, this point on the curve, to this one. And then, when you will relax not exactly, incident resonance. Okay, when you will relax not exactly at the same energy, but you will first relax here to create your vibrational mode, and then relax here to emit a scattering photon. This is first-order resonance. First-order resonance means that you have resonance on one point of the eigenstates of the nanotubes, and one single point of the eigenstates of the nanotubes. And then you can have what we call double resonance. When you have double resonance, it means that you will go on two eigenstates of the nanotubes. So that is, for example, this case here. You go from this point, you absorb light, and you arrive here. And here, this is the first eigenstate of the nanotube, the first resonance. And then, you can imagine you go to another point of the dispersion curve, to another eigenstate. But this cannot happen all time. This can happen only if the electrons are scattered by a defect. So this is at this time, at this moment, that the role of the defect is important. To have this transition from this point to another point on another wave vector of the Brillouin zone, you have to have defects. You have to scatter your electrons on a defect. So if you have scattering of this electron on a defect, it will be able to scatter, to go to another point of the Brillouin zone, to another state, another dispersion curve in the Brillouin zone. Then, if you want to conserve the momentum, because in every interaction between light and matter, you have to conserve momentum and energy. So if you want to conserve the momentum, you must come back here and relax to the initial state. This is called a second order process, or double resonant mechanism, and this is observed only if you have defect in your materials. So the intensity of the corresponding band will be observed only if you have defect, and will increase when the number of defects increase. Because the phonon here has a wave vector q which is non-zero, while here, you know, the q is the wave vector of the phonon. Here the wave vector of the phonon is 0. Here the wave vector of the phonon is non-zero. So because the wave vector here is non-zero, the frequency of the corresponding phonon will be different. So in this case, you will measure a phonon, which is not a phonon of the gamma point of the center of the Brillouin zone, but a phonon of what we called yesterday the K point, the edge of the Brillouin zone. And this is why you have an additional component in your spectrum here at a frequency which is significantly different from the Brillouin center of zone gamma phonons of the corresponding to the first order process. So this was just to explain you that this D band cannot be observed if you don't have defects in your materials. These D bands correspond to a double resonance mechanism. It corresponds to a phonon which is not in the center of zone, which has a wave vector corresponding to the edge of zone, the edge of the Brillouin zone. And we call this peak D band because it can be observed only when you have defects, only when you have FP3 carbons in your sample. So what can we do from that? Well, we can study the intensity of this band with respect to the amount of defect in the sample. So the best example I found was on nanographite. It was not on nanotubes, but it's similar what happens in nanographite. In nanographite, you can irradiate your graphite to create defects with ion beam, for example, high energy ion beams. And you will be able to measure the evolution of the Raman signal with the amount of irradiation. And you'll be able to couple Raman measurements with diffraction measurements. In diffraction measurements, you can measure the coherence length, that is the typical distance between two defects. And this is what you obtain. If you irradiate nanographite, you will create more and more defects from top to bottom. It's more and more irradiated, so more and more defects. And you see that the D band is very small when you have no defects, and then it starts to increase, and when you have a huge amount of defects, the D band is larger than the G band. In nanotubes, you have the same phenomenon. Therefore, you can use the intensity of the band to have an estimate of the amount of defects on your samples.
But the cube or the chip is, but the intensity, the peak is, I think, I don't know, it's changed, no? It's chip.
It's chip?
Chip.
Shifted. This one?
Yeah.
Okay, that's a good remark. That's a good, okay, it should not be shifted in the first approximation, but that's a good remark, and actually I think you're right. For this spectrum, it must be shifted. But for small amount of defect, it's not shifted. Okay, very nice. So we will use, and lots of people use, currently, the intensity of the D-band to estimate the amount of defect. Once again, you have two kinds of defects in a nanotube sample. First, on your nanotube itself, but also on impurities, carbonaceous impurities, which are around the nanotubes. So sometimes it's not that easy to make the difference between the D signature of nanotube defects and the D signature of carbonaceous impurities around. The third and maybe most widely used peak to study nanotubes is this one at very low frequencies. And this one is very specific of single-wall nanotubes. These two can be observed in any form of carbons. Graphite, nanoshells, amorphous carbons, multi-wall nanotubes, any forms of carbon. This one, at low frequency, is very specific of nanotubes. This is corresponding to this motion, which we call a breathing. So imagine you have your tube, which breathes, and which unbraces. The corresponding motion will be a motion of all carbon atoms perpendicular to the nanotube axis, and all the nanotube atoms will move in phase perpendicular to the nanotube axis. And you can quite easily imagine that the energy you have to spend to brace the nanotubes is larger for small nanotubes, because you have to deform nanotubes with a high curvature, than for large nanotubes. And then you can imagine quite easily that the frequency of this mode will depend on diameter. Therefore, if you are able to measure the frequency of this mode, and if you know the relation between frequency and diameter, you will be able to estimate the diameter. This also is quite unusual, using Raman to make a structural measurement. Here, Raman can be used to measure the diameter of the molecule, of the nanotube. Obviously, one key point is to have an accurate relation between frequency and diameter. So, I first show you an example, and then I show you how we can have this relation. So just to fix the ideas, these are two Raman spectra on two different kinds of samples. Here, this is the arc electric samples with nanotube diameter between 1.2 and 1.5. Here, this is a chemical vapor deposition sample with much smaller diameter, but significantly smaller diameters. And here we focus only on the radial breathing mode part, the low frequency range. You can see the Stokes parts, the anti-Stokes parts. You can see that you have several components, not only one peak, but at least two here, which means that you don't have only one kind of nanotubes in resonance, but several kinds of nanotubes. And most important, you can see that if you change the diameter, the position of the peak change. So for small diameters, the radial bracing modes shift to higher energy, to higher frequencies, which confirms you that there is a relationship between frequency and diameter. So now, how can we calculate this relation between frequency and diameter? If you want to calculate that, you have to make two kinds of experiments, Raman and diffraction, either X-ray or electronic diffraction, because diffraction will be the ideal technique to measure the diameter of the nanotube. So if you do that, you can plot a graph where you measure diameter of the nanotube from X-ray diffraction and radial bracing mode from Raman measurement. And you can find that they will go on a line. So you can you can conclude that the relation between frequency and diameter looks like that. Frequency is proportional to 1 over the diameter, proportional to the inverse of the diameter. But since this line doesn't go to 0, you have a second term, and usually this term is assigned to the environment, to the contribution of environment. It means that when you would change your nanotube of environment, go to a liquid phase or a gas phase, put surfactant or different media, this value will change. But actually, we know now that this value will also change. So these two values will depend on the surrounding media around the nanotubes and will be different in gas, liquids, for individual nanotubes or for bundles. So here, this is a result for bundles of nanotubes in air. And this corresponds also quite well to calculations, which is the continuous line. So typically, the frequency will be related to 1 over the diameter, and you will have to determine these two coefficients, which will depend on the details of the environment. This was achieved on macroscopic samples, on powders of nanotubes. But you can also do that, I will show you later, on individual nanotubes. So first of all, before to show you results on individual nanotubes, so we recall that radial breathing mode's frequency will be proportional to diameter, inversely proportional to diameter. But it's not enough to measure the diameter to identify the NM, because you can see it here. For one given diameter, you can find different NM nanotubes. Different nanotubes with different chiral symmetries, different chiral angles, can have the same diameter. So it's not enough to know the diameter to identify precisely, accurately the NM. You need a second information. You need a second parameter. And what is this parameter? It's the transition energy. If you want to identify for sure one nanotube, you must know not only the diameter, but the transition energy. If you know both diameter and transition energy, now you can say for sure which NM nanotube you have. So how can we measure the transition energy in Raman? If you understood what is the resonance phenomenon, you know that when you have a Raman signal, you already can be sure that you are close to the resonance energy. So the laser energy is close to the transition energy. But this is not enough to conclude. You have to know exactly the transition energy, not just to be close, but to know the precise value. So to know the precise value of the transition energy, the precise value of the resonance energy, you can make what we call Raman resonance profiles. What is a Raman resonance profile? It's a measurement of the intensity of the radial breathing mode with respect to laser energy. So for this, usually you use a tunable laser, like a Titan Sapphire laser, where you can tune the laser energy. And you will measure the intensity of the radial breathing mode with respect to the laser energy, and you will find that you have like a Gaussian distribution, a Gaussian evolution, and the maximum will tell you what is exactly the resonance energy, what is exactly the absorption energy of your nanotube. So now, if you are able to calculate the diameter from the frequency of the radial breathing mode, and to calculate the resonance energy from the Raman resonance profile, you have two parameters which allow you to identify for sure the NM nanotube that you have in your sample. So these were measurements on nanotubes individuals, and these were measurements of nanotubes in bundles from the group of Jorio in Belo Horizonte, Brazil. And what you can also observe is that the resonance energy is slightly different when you have nanotubes individual, when you have nanotubes in bundles. It's not exactly the same position. So this is also an illustration of the effect of environment on the electronic properties. Once again, if you want to use the good Catora plot, you have to consider this effect of environment. And here you have an illustration. If nanotubes are individual in solutions, or if they are assembled in bundles in air, they don't have exactly the same transition energy. So in photoluminescence, we saw that we can identify nanotube from the absorption and excitation energy. In Raman, you can also identify nanotube precisely, providing you are able to measure both the radial breathing mode frequency and the resonance energy. Just for illustration, and also because that's like exceptional, like very unusual, I want to show you these results on one individual nanotubes. Here you don't have a sample, you don't have a powder or composite. You have one molecule, one single molecule. And once again, normally in Raman, you will never be able to measure any signal. But in resonance Raman, providing you find the good wavelengths, providing you use the right laser energy, you will be able to measure the signal of only one nanotubes. That's not an easy experiment. First, you have to find the good laser energy, and also you have to be sure to make sure your nanotube is aligned parallel to the light polarization. Otherwise, you will have nothing. So, people in our group in Montpellier are making these very nice experiments. You have also to enhance the signal to have suspended nanotubes. They should not stick on the substrate, otherwise the resonance is smaller. They should be suspended in air. So you have to prepare samples when nanotubes are suspended, and you have to carry out in parallel Raman measurement and electron diffraction measurement. So this is the electronic diffraction pattern of the nanotube. This is the radial breathing mode of the nanotube. So here you will measure the frequency. Because you have a huge signal, you know that you are very close to the resonance energy. I mean, huge signal. That's not that huge, but for one single molecule, that can be considered as huge. And here, you will be able not only to measure the diameter, but also from the electronic diffraction pattern, to measure precisely the NM. So that's an experiment where you can associate for sure one Raman spectra to one given nanotube. And then you can have like a metrology catalog where each nanotube can be identified with its specific Raman signal. So if you do that on several nanotubes, you can plot once again the radial breathing mode frequency with respect to diameter, and you again find a linear relationship, but you see that it's slightly different from the relation before, because here the nanotubes are not in bundle, they are individual. And because they are individual, the frequency, the vibrational frequency, is slightly different. Okay? Since the radial breathing mode is a radial motion, it will be very sensitive to the molecules or to the media which is around. So if you have individual nanotubes or if you have bundle, the frequency will be slightly different. So now we must conclude on this first part. And I must ask you how long time I have. Okay, so I will stop there. So to conclude, we can say that optical spectroscopies are used not only to study vibrational properties, but also to study electronic properties, because you will be able to measure resonance phenomena and to estimate the allowed optical transition, which correspond to the position, the energy of the van 't Hoff singularities in the density of states. And we also saw that each nanotube displays specific signature, so that if you can carry out optical measurements on the sample, you will be able to identify one specific nanotube and detect its NM signature, its NM properties. What about the difference between the different techniques? You see that absorption is first experiment you can carry out. It's probably the most simple to carry out, but it's not the most, it doesn't give the most information, the best information, just because the bands usually are not that much resolved. In one band, absorption band, you have the contribution of several nanotubes, which are quite close one to each other. So it's not that easy to assign each subband to one specific nanotube. By contrast, when you carry out photoluminescence or Raman, you can be sure that you identify precisely NM. In photoluminescence, you do that if you are able to measure two resonance energy, the absorption energy here and the emission energy. And in Raman, you can do that if you are able to measure the frequency of the radial breathing mode and the absorption energy. So I have only 5 minutes. I don't want to go further than that. Maybe the only thing, I will show a very last slide, because I wanted to speak about dispersion, anisotropy, thermal conductivity, but we don't have time. So I will just show you one transparent, which is interesting because it couples Raman and photoluminescence with the same experiment. So it allows, on one single experiment, to measure both Raman and photoluminescence. So you remind that photoluminescence can be observed only when nanotubes are individual, when they are not in contact one to each other. So what happens when you go from a powder, where nanotubes are in contact, to a suspension? So once again, what we call suspension, and Cécile talked about that yesterday, is a system where you were able to disperse nanotubes as individuals. And usually to do that, you use surfactant, soaps, which will surround nanotubes and prevent from aggregation. So what happens when you go from that to that? If you want to see on the same spectrum Raman and photoluminescence, you have to carry out some Raman experiments in the near infrared. So this is 1.16 electron volt, which corresponds to 1064 nanometers. This is a YAG laser. What happens if you make Raman at this wavelengths? You will be in resonance with the nanotubes which absorb at this wavelength. So you will see some Raman signals. You will see the G band here. You will see the D band here. You will see the radial breathing modes. But you will also be able to measure photoluminescence, because photoluminescence, if it occurs in the near infrared, so very close to this energy. So your detector that you use for measuring Raman is also a detector which will be useful to measure the photoluminescence. So this is the scale of the Raman measurements. This is the scale of the photoluminescence measurements, which are carried out with the same detector. So what happens when you disperse nanotubes as individuals? You find the same Raman peaks, here the G band, here the D band, here the radial breathing modes, but you find that superimposed to these Raman peaks, broad peaks, and these broad peaks corresponds to photoluminescence measurements, photoluminescence peaks. So you are able, with such an experiment, not only to characterize your sample, amount of nanotubes with the G band, amount of defects with the D band, diameter with the radial breathing modes, but also to check whether or not your nanotubes are well dispersed. If they are stick together, you won't have these photoluminescence peaks. If they are individual, you will measure these photoluminescence peaks. And the last thing I want to show you is that this photoluminescence peak, as you can see here, are shifted from this sample to this samples. And here, the only difference between these two samples is that we use different surfactants. Here, it's a small molecule surfactant, small ionic surfactant, SDS, sodium adenylyl sulfate. And here, it's DNA. It's short single brands of DNA that can be used also as surfactant. And once again, you observe that the photoluminescence shifts are shifted, which means that the optical energies are slightly different which means that the resonance energies are slightly different. And this is once again a confirmation that the optical and electronic properties are very sensitive to the environment of the nanotubes. I will finish there. This is the photoluminescence map on the same systems, but we don't have time to go in the details. We can do that on suspension, but also on composites. So this is a composite matrix, polymer matrix composites, where you can see the same photoluminescence peaks and the same shift between the peaks when you go from SDS to DNA or from water to polymer. So photoluminescence here is used as the powerful tool to have an idea of the effect of the environment and to detect each NM nanotubes which are in the samples. In addition, when you have this photoluminescent signal, you can be sure that both in the water and in the polymer, you have individual nanotubes which are not connected to each other. So I won't have time to show you all this. I will just go to the conclusion. So in the conclusion, I hope I convinced you that different optical spectroscopic techniques, and first of all, photoluminescence and Raman, are useful to study the vibrational properties of the nanotubes, but also their electronic properties, and that you can have very interesting information on the structure and go up to the identification of the precise NM integrals for each nanotube in your sample, either in a composite sample or even for one individual nanotube. We saw also that thanks to photoluminescence measurement, you can have information on the dispersion, the good quality of the dispersion of the nanotubes in your samples. And we didn't have time to show, but it's true also that you can have information of the orientation of the nanotubes because the signals are very polarized. So you can use polarization measurements to detect the orientation of the nanotubes. You can follow the kinetic growth during a CVD measurement. You can even measure thermal conductivity in Raman because you have a thermocouple in the Raman. You have a measurement of the temperature. So you can absorb light from the nanotube and then measure the change of temperature with respect to time with the Raman. So you can have measurement of thermal conductivity directly under your micro Raman. Thank you very much for your attention, and I'm open to questions. And this guy can translate the questions in Spanish, like Anwar did yesterday. Yes.
Primero la dama.
No se observa, o sea, ninguna interferencia de lo que es impureza o otro defecto que tenga.
Pourcentage de nanotubes.
La pregunta es si hay diferencia entre los nanotubos y las impurezas que hay en la misma muestra.
Sí, porque ¿qué porcentaje de impureza tiene ese nanotube de
The question is what is in the nanotube?
Yeah, that's okay. So, obviously, it depends on the samples. At the beginning, where the first nanotubes samples came, it was maybe 1% or less of nanotubes. But now, there have been big progress in synthesizing, growing nanotubes, and also big progress in purifying the samples. So now you can have samples where you have, I don't know, maybe 15 weight % of nanotubes, which is quite high because you always have some metallic particles which are quite heavy. So if you have 51% of nanotubes, it's already a very, very good sample. And as far as spectroscopy is concerned, the key point for the answer is that only nanotubes are resonant. The metallic particles are not, and the other carbonaceous species are not resonant as nanotubes. So we estimate that the resonant enhancement of nanotubes with respect to graphite, for example, is at least of 100, or amorphous carbon, if you like. So if you have only 1% of nanotubes and 99% of amorphous carbon, you will have the same answer. So you need to have 100 times more impurities than nanotubes to see them at the same level of intensity. So when you have a 50% sample, 50% nanotube, 50% impurities, you don't see the impurities at all. They are much smaller, they have much smaller intensity, you cannot see them. So it's very selective. These techniques are very selective for the nanotubes because of resonance.
Bueno, voy a decir en español. Para todos estos gráficos, los resultados que se ven, lo que yo entiendo, mi poco conocimiento, cuando hace la radiación a seco monocromática, monochromatic waves.
For Raman, yes.
And, pues, si apunta a la muestra le da unos resultados que van cambiando. Si usa diferentes ondas, o sea, policromáticas, no tendrán resultados similares, pero le den alguna información.
If you can do that.
Question that have a laser with monochromatic wavelength has an interaction with the sound. Right? If you change the wavelength, if you use polychromatic radiation, would you get some changes that would bring you some information?
Actually, in Raman, you cannot do that. Because in Raman, one issue is elastic scattering. So, la question c'était en même temps ou l'une après l'autre? Yes, you can. So the question is, je peux dire en espagnol peut-être? So, about multi-wall nanotubes, it can be obviously used, studied by these different techniques, but it's much less ideal structure because you can define an NM for each single wall, but for multi-wall, if you want to define it, you have to know the NM of each layer, and that's almost impossible if you have more than 2 or 3 layers. So in multi-wall, I don't speak about double wall, because double walls are very interesting. They are not only interesting because they are also like model, but also because you can make lots of chemistry on them. And if you make chemistry on the outer shell, the inner shell is still intact. So double wall are very nice materials. But if you are multi-wall, usually you won't see that because the resonance will be decreasing with the diameter, and when you have multi-wall, if you have more than 10 shells, the outer diameter is above 4 or 5 nanometers, and then you don't have resonance anymore. So in multi-wall, what people do usually is to measure this G-band, this D-band, so that they have an idea of the amount of nanotubes from the intensity of G-band, because this band, its intensity is proportional to the mass of the sample. And they look at the amount of defects. So you can, for example, see that when nanotubes, multi-wall nanotubes are prepared by CVD, they have much more defects, usually, than they are prepared at high temperature by electric arc technique, etc. And then if you want to purify your sample by heating or by acid, etc., you will be able to check whether or not they are purified, whether or not you eliminate the impurities, and you anneal the defect with these bands. But this band, usually you won't be able to measure.
Dependiendo de las impurezas que posee el nanotubos, por ejemplo, impurezas metálicas, las bandas RBM, P y G se desplazan. Si ustedes están tabulados estos valores, se desplazan esas bandas dependiendo de la impureza metálica que tenga el nanotubos. Dependiendo de las impurezas que presenta el nanotubo, por ejemplo, si es una impureza de algún metal, las bandas RBM, P y G se desplazan en el espectro humano. Están tabulados esos datos.
Yeah, the question is, if you have metallic impurities, will that move the position of the different Raman bands?
Okay. So the answer is no in general, because it's no as long as you don't have change of the electronic properties of nanotubes. So if you have one metallic particle and your nanotubes, which is stick only at the extremity, and you have no charge transfer, there is no effect on the Raman. But if you have some charge transfer, and it can occur with some specific metallic compounds, and Alain will talk a lot about that now. If you have charge transfer, yes, this time you will have an effect on the electronic properties, and therefore also an effect on the optical properties. But only in case of oxido-reduction relationship, not in case of the copper, cobalt, nickel, or iron particles that are used for synthesizing. So the answer is no. In general, you don't have any effect.
Más o menos estaba relacionada la pregunta igual, sobre todo mi mayor interés era la calidad de vida o la calidad de la propiedad óptica del nanotubos. ¿Qué velocidad tiene? ¿Cuánto vive esa propiedad óptica del nanotubo? Porque normalmente siempre con lo que manejan las impurezas, entonces se va perdiendo. Y yo quería que me hablara más o menos de la calidad de vida, de que se pueda apreciar eso. Más o menos ahí cuando él habla de que no han tabulado, yo entiendo que eso no lo han evaluado.
The question, I understand well, the question about the lifetime of these properties of nanotubes, and will they change with time and with the amount of the impurities changing with time.
You mean if the sample evolutes as an evolution with the time? Normally, okay, nanotubes are very reactive because of their high surface, but they are also very stable because the sp2 bonds are very stable. So if you just let them in air at room temperature, they will not evolve. But if you heat them under oxygen, or if you are in an acid atmosphere, a special atmosphere, they can evolve. But a sample of nanotubes in air, to my knowledge, it will not evolve that much. I must say that there are significant changes from vacuum to air, because oxygen and water will stick, and there it will change slightly the properties. So yes, if you prepare nanotubes in vacuum, then put it in air, it will change. But then, if it stays in air, it will not have significant evolution.
The question she wants confirmation that the Raman spectrum will tell her about the diameter of the nanotube, and depending on the diameter, that will tell her the optical properties of the nanotube.
Yes. The length, no. So first, the longitude. Okay. So for the longitude, the answer is no. You don't have any idea of the longitude, except if the longitude becomes very small. But very small means a couple of nanometers, so it's not a nanotube anymore. But for the diameter, the answer is yes, but be careful. If you use only one wavelength in Raman, you don't see all the nanotubes in your samples. You see only the nanotubes which are in resonance. So it's not because you don't see the signature of one nanotube that it means that it's not here. Maybe it's just that you didn't use the good wavelength. See?
Okay. ¿En las otras sedes tienen alguna pregunta? Mérida, Ivy. Ivy, ¿me estás escuchando? ¿Tienes preguntas?